Greetings from Melbourne, Australia. My name is Emanuele Viterbo, and I'm a professor at Monash University, Clayton. I would like to thank the organizers for inviting me to deliver this talk on OTFS versus OFDM performance complexity trade-offs. I would also like to thank my collaborators, Taraj Taj, Ravi Tejapachava, and Yi Hong, who have been working with me on OTFS for the past 3 years. OTFS is a recently proposed two-dimensional modulation scheme where the information symbols are multiplexed in the delay-Doppler domain. Now, the delay-Doppler domain is closely related to the physical geometry of the wireless channel. If you look at these two pictures, there you can see the multiple paths connecting a base station to this gray car, and each path has a different, obviously, length, but also is affected by different Doppler shifts due to the moving scatterers in the seam. So the delay-Doppler plane will represent the different paths and the different delay shifts of each path. The following diagram shows the operation of an OTFS modulation and demodulation. As you can see, there are three domains. The outer domain is the delay-Doppler, and that's where the symbols, information symbols are located at the transmitter and where they are recovered at the receiver. Now, the principle of operation of OTFS is represented by the following blocks. So the delay-Doppler is transformed by a two-dimensional inverse symplectic Fourier transform to the frequency-time plane. Now, the frequency or time-frequency plane is then converted to a time domain signal and transmitted over the channel. The channel is a time-varying channel due to the presence of Doppler shifts. The received signal is then converted back to time frequency, and the time frequency is converted back to the delay-Doppler domain. Detection can occur in the delay-Doppler domain in order to recover the information transmitted in the delay-Doppler plane at the transmitter. So here you can see how the two-dimensional modulator operates and how the receiver, the match filter receiver, two-dimensional match filter receiver operates. These are based on the two pulses, which are the pulse shaping waveforms, GTX and GRX, which, if they are perfectly biorthogonal, that is orthogonal both in time and frequency, by time and frequency shifts, then we are in the ideal situation where the input-output relation in the time-frequency domain is very simple. We have a single tap effect of the channel in time frequency on the transmitted samples in time frequency, and you have the received samples in time frequency. So the relation for ideal pulses, perfectly biorthogonal pulses in the time frequency domain, is very simple. Single tap operation. The channel affects symbol by symbol independently. If we look at this relation in the delay-Doppler domain, this corresponds to a two-dimensional circular convolution of the channel delay-Doppler response with the data in the delay-Doppler domain. Now, this is not the case if the pulses GTX and GRX are not perfectly biorthogonal. And this is the case for any actual pulses, because no pulse will be perfectly concentrated in both time and frequency. They can be approximately concentrated in time and frequency, but whenever that happens, there will be some interference along the time or the frequency domain, and hence a loss of orthogonality. So in the special case where the pulses are rectangular, we have a simple input-output relation in the delay-Doppler, which resembles this two-dimensional convolution, with an additional twist due to these phase corrections, which modify the two-dimensional convolution, circular convolution, into this twisted two-dimensional circular convolution. Here we assume we have a number of delay paths, and then for each delay path we may have a number of Doppler paths. So this is the corresponding convolution. The VL kappa is the representation of the channel coefficient for the Doppler shift kappa and delay L. We have seen the principle of operation in the previous diagram, but for a practical implementation, that same operation can be achieved in a much simpler format. And here is you can see in this diagram that the delay-Doppler plane, where the information symbols can be placed in this two-dimensional array, are subject to an endpoint inverse fast Fourier transform on each row, and to convert that into the delay time plane. The delay time plane is then vectorized, so column-wise, and then transmitted sequentially as the time domain signal. This time domain signal goes through the time-varying delay time channel, and at the receiver, their inverse operations are performed, and the delay-Doppler domain detection is performed, which consists in deconvolution of the two-dimensional circular twisted convolution. So this slide visualizes the difference between the OTFS transmitter and an OFDM transmitter. So in OFDM transmitter, we start from the time frequency plane. We place our information symbols in this time frequency plane, and then we apply OFDM modulator on each column. And the result is transmitted and vectorized and transmitted in the time domain. What's the difference? Well, the complexity of the transmitter difference relies on the numbers for M and N. The M is the number of subcarriers in OFDM, N is the number of copies of OFDM symbols that are transmitted. To be more precise, we know that OFDM relies on the use of a cyclic prefix, and in fact we can add the cyclic prefix down here in the time domain, and the similar cyclic prefix or a zero padding is added for the OTFS, can be added for OTFS. The receiver of OFDM and OTFS can be compared in a similar way here, where the inverse operations are performed. And for OFDM, as we know, we can operate in the time frequency and do single tap equalization. In OTFS, we will have to do some extra operation to extract the information symbols. But if we just look at the receiver complexity without the detection, essentially we are mirroring the same complexity as the transmitter. This slide shows the input-output relation for both OTFS and OFDM in the vectorized format. Now, as you can see, in the case of OFDM, the operations can be performed on blocks M by M, while in the case of OTFS, we can operate on blocks N by N. Now, the presence of the addition of a CP or a ZP in general enables to remove interblock interference in OFDM. In OTFS, it has the advantage of making this matrix a lower triangular and simplifying the detection. So let's have a look at the specific OTFS signal detection. When we look at the input-output relation in the delay-Doppler domain, we've seen it's a twisted two-dimensional convolution. We can represent that in a matrix form where the received vector y is a matrix H times X plus noise. where the matrix H represents gives the delay-Doppler domain behavior. Now, obviously, this matrix is NM by NM, which is a large matrix, but it is very sparse. So we have proposed the iterative Rake decision feedback equalizer, which solves this problem and extracts the good estimates of the transmitted symbols in X, taking advantage of the structure of H and its sparsity. In particular, the fact of adding the zero padding to OTFS enables us to simplify the detection and make it operate on a block-by-block basis. And we have M blocks of each of size n by n. The maximal ratio combining operation performed by the iterative Rake decision feedback equalizer, it can be represented in this graph, and takes advantage of previous decisions to update the successive ones, as in decision feedback equalization. And it combines the estimates from multiple received samples and to improve the estimate of the symbols. This algorithm is iterative in nature and benefits from having a good initial point to start from. This initial estimate can be performed in the time frequency domain by a single tap equalization, which we know is affected by interference. But it gives a good starting point for the iterative algorithm to converge faster. Here we compare the performance of OTFS versus OFDM in the presence of a multipath channel model by the EVA channel model, where we have 8 delay paths and we have user equivalent speed spread up to 120 kilometers per hour. You can see that the different modulations, 4 QAM and 16 QAM, show the improvements of OTFS versus OFDM. You can also notice that the simple detection performs as well as the best known detection based on the message passing algorithm, but with a much lower complexity, as we will discuss later. In summary, zero padded OTFS in conjunction with the iterative decision feedback detector based on maximum ratio combining is effective in high mobility channels and outperforms the OFDM solution. Further improvement in performance can be achieved by concatenating error correcting code and applying the turbo principle, as illustrated in this figure. This slide shows the coded performance with the rate 1/2 LDPC code of OTFS versus OFDM. And we can see when a single pass of the decoder is performed, there is a gain of about 4 dB for a 16 QAM and a bit less than 4 dB for a 64 QAM between the OFDM with red curves and the blue curves. The additional gains can be obtained by adding turbo iterations. This slide shows the complexity in terms of complex multiplications of OFDM and OTFS, and the take-home message could be summarized in the following example, with a size of 512 by 128 and L paths with high mobility. We achieve a 4 dB gain with a 16 QAM at the cost of a complexity which is 4 times the complexity of OFDM. On the other hand, on a low mobility channel, the OTFS detection can be simplified, and the actual performance gain is achieved with only 2 times the complexity of OFDM. I would like to conclude with an update, a recent result, where we have proposed an alternative version of OTFS, where instead of using Fourier transforms in the Zach transform, we're using Hadamard transforms, with the advantage of further reducing the complexity and without losing performance over OTFS. Thank you for your attention, and I'm happy to have your questions.